Okay, in this part of the Introduction to Active Filters lectures, we're going to discuss bandpass and band reject filters. And so first let me say that the bandpass filter, because it has two cutoff frequencies, an upper and a lower, and same with the band reject, they're actually considered second order filters because you'll find in the denominator of the transfer function we have a quadratic. So technically that's considered a second order filter. In this case, the second order filter gives rise to two different cutoff frequencies, one on the lower end and the other on the higher end. Now, in the previous chapter, we discussed a bandpass filter made out of three active elements, an inductor, a resistor, and a capacitor. Three passive elements, an inductor, a resistor, and a capacitor. In this chapter, we're talking about active filters, and so the bandpass filter will actually be constructed of two op-amp filter circuits that are cascaded with one another. Now, the important thing to remember here is that the ideal op-amp has an infinite input impedance, and so because of that, op-amp circuits can be cascaded without one loading the other. In other words, it's not like if we were to add a bunch of extra resistors and capacitors onto a passive circuit where that would draw additional current. The infinite input impedance creates a situation where the transfer functions basically will multiply with each other in the Laplace domain. Now, because of this feature, we can create a bandpass filter by cascading a high-pass filter and a low-pass filter. And so what will happen is the transfer functions will multiply, giving us a bandpass filter. So it's easier to get some of these concepts if we look at an illustration. So here was the magnitude versus frequency plot on a logarithmic scale for a high-pass filter, and here it is for a low-pass filter. Now let's think about what could happen if mathematically we multiplied these two graphs together. So in the first place, a gain of 0 dB corresponds to a gain of 1 in a ratio scale. So in the middle part between the lower cutoff and the upper cutoff, we would have 1 times 1. So we would just have, in this range in the middle, we would have a flat section with a magnitude equal to 1. Now on the lower frequency end, the higher pass filter is rapidly transitioning to a gain of 0. So basically from this diagram we still have a behavior existing for lower frequencies. It's just it levels out at 1. So on the low frequency ends we'd have this slope from this graph multiplied by 1 from this graph, meaning basically on the lower frequency end we'll just duplicate this slope. Same is true on the higher frequency end. On the higher frequency end, the high pass filter has a gain of 0 dB or 1. So that's going to be flat, and so if we multiply 1 by this slope, this negative slope, we'll just get the negative slope behavior back. So basically if we take the product of the magnitude behavior on the high pass filter and the magnitude behavior on the low pass filter, we'll get a bandpass filter. So in order to construct this circuit, what we need then is we need a low pass filter and a high pass filter and an inverting amplifier cascaded together. Now what do we mean by cascaded? We mean the output of the first is connected to the input of the second. So if we look at this first circuit, this is our low pass filter. Here would be the output right here. And so we'll be able to calculate a cutoff. And notice here that the input and the feedback impedances are set to be equal. This is for ease of design so that you don't have to use as many different resistor values, and so that you design your low pass and your high pass both to have a gain of 1. Then any gain greater than or less than 1 is accomplished with this last stage, which is simply an inverting amplifier that has a flat frequency characteristic. So in other words, it's going to take whatever is present from the transfer function from these two and multiply by a constant. This could be 1. You don't necessarily even need this stage if you don't want to change the gain above or different from 1. So we have this first stage, which is a low pass filter. The cutoff again would be 1 over RC, where we have RL and CL. So you need a unity gain low pass filter, and the low pass filter is going to actually form the upper cutoff frequency omega C2. So this is a little counterintuitive. The high-pass filter will have a cutoff frequency that is on the lower end, omega C1, so the smaller of the two. So basically, you just, for your design, you set 1 over RLCL equal to omega C2, and 1 over R high C high equal to omega C1. And then if you need to make a gain adjustment because of design specifications, you can do that using this last stage inverting amplifier. So that's how you accomplish the transfer function that will give you a bandpass filter. And let's look at what that looks like. First of all, we'll look at the plot. So this end is the behavior of your high-pass filter, and notice that the high-pass filter determines the lower cutoff frequency. This is the behavior of your low-pass frequency. It's going to determine the upper cutoff frequency. Once again, this is plotted on a log scale along the horizontal axis, and the vertical axis isn't shown, but it would be plotted on a dB scale, linear scale, with the units being dB. Okay, couple of things. First of all, when we build a filter like this, it's important, if we're going to design it by cascading a low pass and a high pass filter, that we're building what is known as a broadband bandpass filter. And broadband is roughly defined as the ratio of the lower to upper cutoff frequency, upper to lower cutoff frequency has got to be greater than or equal to 2. So in other words, your upper cutoff frequency needs to be at least 2 times as large as your lower. Now let's go back. So in other words, this needs to be a factor of 2 above this. Now the reason that that's important is if you could visualize that suddenly we make omega C1 and omega C2 get closer and closer together, you can see how in this, as we're at the knee, sort of the cutoff frequency here and here, we're less than 1 on our gain. So if these 2 points approach one another, then what we have is this curve multiplying this curve in the middle, not where they've approached a gain of 1, but where they're down here below 1. And so what that would mean is this curve, the whole thing would be kind of reduced. You wouldn't have a constant gain region in the pass band, but rather you would have a reduced gain because you allowed these two to get too close together. So once again, definition of broadband is that the ratio of upper to lower cutoff frequencies be greater than or equal to 2. And that's a formal definition, so that's kind of accepted throughout the field. All right, so we would find the transfer function then by taking the ratio of V out over N over V in. And remember, it's basically the product of these 3 components. So here is our low pass filter, here is our high pass filter transfer function, and here is our gain transfer function. So the transfer function overall would be the product of all 3 of these. And so we can express that as a single transfer function, where in the numerator we would have k times omega C2, where k is this ratio, the gain ratio of R feedback to R input. And then in the denominator, we basically have the product of the lower frequency cutoff, the pole at the lower frequency cutoff, and the pole at the upper frequency cutoff. So when we simplify that, we end up with something that is a constant times S over this quadratic. Now, this is going to be quite different from the transfer function that we got for the RLC bandpass filter. So here was the transfer function we got from the RLC bandpass filter, where we had beta S in the numerator over S squared plus beta S plus omega naught squared in the denominator. So first of all, just going back and looking, this is our new transfer function, and you'll notice that that while this can be defined as omega naught squared, this is not the bandwidth, and this is not the bandwidth. So it's fundamentally physically a different circuit, and the transfer function hence looks different. Now, the op-amp circuit will approach the bandpass filter circuit that we saw in when we were doing passive filters if omega C2 is much, much greater than omega C1, in which case the bandwidth can be approximated as omega C2, and this does then reduce to something close to what we had in chapter 14. However, this is not a good approximation to make. The other issue is that, remember, the maximum gain you can have on a passive filter is equal to 1. On the active filter, we can set our gain based on either the input and feedback resistors of the high and low pass filters, or based on that third inverting amplifier that we set to be a gain not equal to 1. So this is your design equation for the passive RLC filter. This is your design equation for the cascaded op-amp filter, where you would just have two RC op-amp filters, one being a low pass, one being a high pass, and then if a gain is desired, you add that third stage. So once again, let's go back and look at that figure. Here is our low pass, here is our high pass, here's our inverting amplifier. So I do get questions sometimes from students asking me, is there a particular order that it's better to use? Should you put the low pass first and the high pass second, or vice versa? From a mathematical point of view, no, there's not a difference. From an experimental point of view, I could make an argument that in a design you would want to put the low pass filter first, because then you've already filtered out the noise. And so the high pass filter then isn't outputting all of that noise to the low pass filter. So I could maybe make an argument it's better to put the low pass filter first. Certainly it's better to put both of them first before putting in the inverting amplifier, because it has less work to do. And you know how it is. Those of you who've taken lab, in the lab when you actually assemble things, they often tend to function differently than the mathematics models. So yes, maybe there are some arguments to be made for putting it in this order. All right, so that is the bandpass filter. The next thing we want to look at is the band reject filter. Now, the band reject filter works very differently. All right, let's go back. So the first thought that you might have is, oh, well, on the band reject filter, let's just make this one be the upper cutoff instead of the lower, and this one be the lower cutoff instead of the upper. The problem with that is, if you flip omega C1 and omega C2 and try to model this as the product. So let's go. All right, so let's see what happens if omega C1 moves up here and omega C2 moves down here. The problem with that is the cutoff region of the high pass filter is now going to multiply the passband part of the low pass filter by a number equal to almost 0. So if you try to build a band reject filter using the same circuit from which we constructed our bandpass filter, in other words, cascading our circuits together and letting them multiply each other, then instead of having a region in the middle, when you flip your omega C1 and omega C2 to low and high pass respectively, then what happens is everybody just zeroes out everybody else. So you can't build that kind of circuit for a band reject. Instead, what you have to do is you basically have to take the sum of those two filters. So remember that we had a summing amplifier, and we had we showed that we had some input to R1 and some input to each of these resistors, and then we had a feedback resistor, and this effectively summed the inputs to each of these input resistors. So if we look at that, basically from this circuit we get a transfer function, and from this circuit we get a transfer function. And so at this point what we've actually done is we've summed the inputs of a low pass filter and a high pass filter. So we have a low pass filtered signal coming in and a high pass filter signal coming in, and those are added together. And then the feedback resistor basically adjusts the gain between feedback and input. Notice the two input resistors are set to be the same in the summer. That's so that we're not amplifying one of the signals over the other. They're basically both going to come in, go through this inverting amplifier with the same gain ratio. So if you write that down, here's our low pass filter transfer function, here's our high pass filter transfer function. We're adding them together, and if we do some simplification, we end up with the transfer function shown in this figure. So basically what you're doing there is you're taking this one and you're adding it to this one, and the cutoff frequency here on the high pass filter is at a higher level. So you can see when you add 0 dB or 1 to a highly attenuated signal, you're going to remain at 1. When you're at high frequencies and you add 1 to an attenuated signal, you're going to end up at 1. In the middle, you're adding going to 0 plus going to 0, so you're going to get that dip in the middle. And so here's what that looks like, and this illustrates, and in my opinion, kind of badly, what exactly is going on. So here is the transfer function. Basically, this is going to be a summing operation. So we've got transfer function 1 plus transfer function 2. Okay, transfer function 1 looks like this. Transfer function 2 looks like that. You take the sum of this curve and this curve, you end up with this curve in the middle. In this particular example, the feedback to input ratio was set to be 10. And so what the gain does is the gain illustrates in dB the ratio of RF over RI. So it would be 20 log RF over RI in dB. In this particular example, that turns out to be 20. You could set it to be anything. The effect of the gain is it takes what would have been a sum that looked like this, and it multiplies the whole curve by the gain, in this case 20 dB. So the curve is going to shift up. Everybody's going to shift up. So in the passband portions, we would have 20 dB at low frequencies, 20 dB at high frequencies, and then in the middle we have this band reject region. The band reject filter, like the band pass filter, is technically designed to be a broadband band reject filter. If you want a very narrow band reject filter, like say you're rejecting 60 hertz, then that's a different sort of circuit, because this one is designed to work as a broadband. Once again, if these two curves, omega C1 and omega C2, if they get too close together, then out here in the passband region, you're not gonna have quite the same behavior. Okay, that concludes the theoretical discussion of bandpass and band reject filters, and we'll look in the next lecture at some examples as well as some of your homework questions and discuss how those would be worked when doing design. But basically, this section of filter design, the low pass, the high pass, the band pass, and the band reject, is really straightforward. You just look at your circuits, your low and your high pass circuit. You figure your necessary R and C to give you the cutoff you want. And then if it's a band pass or a band reject, you arrange your circuits in the correct configuration. So nothing really complicated about that other than remembering what circuit constitutes low pass and what circuit constitutes a high pass.